following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
So I'm thinking of large, sparse matrices. So the point about the kind of matrices that we've been writing down, maybe two-dimensional, maybe three-dimensional difference matrices. So it might be 5 or 7 non-zeros on a typical row. And that means that you don't want to invert such a matrix. These are big matrices. You know, the order could easily be 1,000,000. What you can do fast is multiply A by a vector. Because multiplying a matrix, sparse matrix by a vector, you only have maybe 5 non-zeros times the n, the vector of length n. So say 5n operations. So that's fast. So, and I'm thinking that we are at a size where elimination, even with a good ordering, is too expensive in time or in storage. So I'm going from direct elimination methods to iterative methods. Iterative means that I never actually get to the perfect answer x, but I get close, and what I want to do is get close quickly. So a lot of thought has gone into creating iterative methods. I'll write down one key word here is part of the decision is to choose a good preconditioner. I'll call that matrix P. So it's a matrix that's supposed to be that we have some freedom to choose, and it very much speeds up. So the decisions are what preconditioner to choose, a preconditioner that's somehow like the matrix A, but hopefully a lot simpler. And which of these methods, well, there are a bunch of iterative methods, and that's what today's lecture is about. Multigrid is an idea that just keeps developing. It really is producing answers to very large problems very fast. So that will be the following lectures. And then come these methods. Well, you may not be familiar with that word Krylov. Let me mention in this family, the best known method is called conjugate gradients, the conjugate gradient method. So I'll just write that down, conjugate gradient. So that will come next week. That's a method that's a giant success for symmetric, positive definite problems. So I don't assume in general that A is symmetric or positive definite. Often it is if it comes from a finite difference or finite element approximation. And if it is, then conjugate gradients is highly recommended. So I'll start with the general picture. Let me put the general picture of what an iteration looks like. So an iteration computes the new x. Let me call it x new or xk plus 1 from the known x. So we start with x0, any x0 in principle. It's not too important for x0 to be close. In linear methods, you could start even at 0. In nonlinear methods, Newton methods, you do want to be close. And a lot of attention goes into a good start. Here, the start isn't too important. It's the steps that you take. And so I guess I'm going to, I'm trying to solve AX equal B. And I'm going to split that equation into, I'm just going to write the same equation this way. I could write it as x equals I minus a x plus b. That would be the same equation, right? Because x and x cancel, ax comes over here, and I have ax equal b. So that's I've split. I've split up the equation. And now, actually, let me bring, so that's without preconditioner. You don't see a matrix P in that. That's just an ordinary iteration, no preconditioner. The preconditioner will come, I'll have P, and it'll go here too. And then, of course, I have to change that to a P. So that's still the same equation, right? Px is on both sides, cancels, and I have ax equal b. So that's the same equation, but it suggests the iteration that I want to analyze. So on the right-hand side is the known. Approximation. On the left side is the next approximation, xk plus 1. And I multiply by p, so the idea is p should be close to a. Of course, if it was exactly a, if p equaled a, then this wouldn't be here, and I would just be solving in one step, ax equal b. So p equal a is one extreme. It's totally perfectly preconditioned, but the point is that if p equals a, we don't want to solve that system. We're trying to escape from solving that system, but we're willing to solve a related system that is simpler. And why simpler? Well, here are some possible preconditioners. P equals the diagonal. Just take the diagonal of A. And that choice is named after Jacobi. So that's Jacobi's method. And actually, it's already a good idea, because the effect of that is somehow to properly scale the equations. When I had the identity here, I have no idea whether the identity and A are in the right scaling. A may be divided by delta x squared or something. It could be, totally different units. But P, if I take the diagonal of A, at least they're comparable. Then you see what? Well, we'll study Jacobi's method. So that's a very simple choice. Takes no more work than the identity, really. Second choice would be, so that would be P for Jacobi. A second choice that you would think of pretty fast is the diagonal and the lower triangular part. So it's I'll say the triangular, I'm going to think lower triangular part of A, including the diagonal. And this is associated with Gauss's great name and Seidel. So that's the Gauss-Seidel choice. So why triangular? And we'll analyze the effect of this choice. Well, because if P is triangular, then we can solve. Right, then there's, I'm never going to write out an inverse matrix. That's understood. But I can compute the new x from the old x, just by back substitution. I find the first component of x, k plus 1, then the second, then the third. It's just because the first equation, if P is triangular, the first equation will only have one term on the one new term on the left side, and everything else will be over there. And the second equation will have a diagonal and something that uses the number I just found in the first, for the first component and onward. So, in other words, triangular matrices are good. Well, then people thought about combinations of these. I'll put a big lot of activity went in something called over-relaxation, where you had a weighting of these, and it turned out to be, if you adjusted the weight, you could speed up the method. Okay. Sometimes called SOR, successive over-relaxation. So, like when I was in graduate school, that was the sort of the beginning of progress beyond Jacobi and Gaussseidel. And then after that came a very natural ILU is the next one that I want to make. So it's the I stands for incomplete LU. So what are L and U? That's the letters I always use as a signal for the lower triangular and upper triangular factors of A. The ones that exact elimination would produce. But we don't want to do exact elimination. Why? Because non-zeros fill in. Non-zeros appear in those spaces where A itself is 0. So the factors have many more non-zeros than the original A. They're not as sparse. So the idea of incomplete LU is, and I'll come back to it, the idea of incomplete LU, you might say, should have occurred to people earlier. Only keep the non-zeros that are non-zero in the original A. Don't allow fill-in, or allow a certain amount of fill-in. You could have a tolerance, and you would include a non-zero if it was big enough. But the many, many small non-zeros that just fill in and make the elimination long, you throw them out. So P is, in this case, P is L is an approximate L times an approximate U. So it's close to A, but because we've refused some of the fill-in, it's not exactly A. And you have a tolerance there where if you set the tolerance high, then these are exact, but you've got all that fill-in. If you set the tolerance to 0, well, you've got the other extreme. Okay. So that would give you an idea of preconditioners, of reasonable choices. Okay. Now I want to think about, well, first, how to decide whether the x's approach the correct answer. I need an equation for the error, and because my equations are linear, I'm just going to subtract. P x, I'll subtract the upper equation from the lower one, and I'll call the error, EK, will be x minus the true answer. This is x exact minus x, my case approximation. So when I subtract that from that, I have EK plus 1. And here I have P minus A. When I subtract that from that, I have EK. And when I subtract that from that, 0. So very simple error equation. So this is an equation, this would be the error equation. Okay. You see the B has disappeared because I'm only looking at differences now. Okay, so that, let me write that over on this board. In even slightly differently. Now I will multiply through by P inverse. That really shows it just so clearly. So the new error is, if I multiply by P inverse, so P inverse times P is I, and I have P inverse A, EK. Clear. So what does that say? That says that at every iteration, I multiply the error by that matrix. And of course, if P equals A, if I pick the perfect preconditioner, then P inverse A is the identity, this is the zero matrix, and the error in the first step is zero. I'm solving exactly. I don't plan to do that. I plan to have a P that's close to A, so in some way, this should be close to I. This whole matrix should be close to zero. Well, close in some sense. So let me give a name to that matrix. Let's call that matrix M. So this is that's the iteration matrix, which we're never going to display. I mean, it would be madness to display. We don't want to compute P inverse explicitly or display it, but to understand it, to understand convergence or not convergence, it's M that controls everything. So this is what I would call pure iteration, or maybe another word that's used instead of pure is stationary iteration. What does stationary mean? It means that you do the same thing all the time. At every step, you just do the same, use the same equation. Where these methods will be smarter. They'll adapt, they'll use more information, they'll converge faster, but this is the simple one. And this one plays a part in those. Okay, so what's the story on convergence now? What about that matrix M? If I take a starting vector, E0, and my initial error could be anything, I multiply by M to get E1. Then I multiply M by M again to get E2. Every step I multiply by M. So after K steps, I've multiplied K times by M. And I want to know, so the key question is, does that go to zero? So the question, does it go to zero? And if it does, how fast? Well, let's ask first, well, the two parts, does it go to zero and how fast, are pretty much controlled by the same property of M. So what's the answer? When does, I don't know anything about E0. So what property of M is going to decide whether its powers get small, go to zero, so that the error goes to zero? That's convergence. Or maybe blow up, or maybe stay away from zero. What controls it? Okay. One word is the answer. Yeah. The eigenvalues. It's the eigenvalues of M. And in particular, it's the biggest one. So because if I have an eigenvalue of M, as far as I know, E0 could be the eigenvector, and then every step would multiply by that eigenvalue lambda. So the condition is that all eigenvalues of M have to be smaller than 1. And in magnitude, of course, because they could be negative, they could be complex. So that's the total condition. That's exactly the requirement on M. And how do we say how fast they go to zero? How fast, if all the eigenvalues are below 1, then the slowest convergence is going to come when, for the eigenvalue that's the closest to 1. So really, it will be, and this is called the spectral radius. And it's usually denoted by a Greek rho of m, which is the maximum of these guys. It's the max of the eigenvalues. And that has to be below 1. So it's this number. It's that number. Because it's that number which really says what I'm multiplying by at every step. Because most likely, E naught, my initial unknown error, has some component in the direction of this biggest eigenvalue, in the direction of its eigenvector. And then that component will multiply at every step by lambda, but that one will be the biggest guy, rho. And so it's the maximum eigenvalue. That's really what it comes to. What is the maximum eigenvalue? Let me take Jacobi. Can we figure out the maximum eigenvalue for Jacobi? Well, of course, if I don't know anything about the matrix, I certainly don't want to compute eigenvalues. I could run Jacobi's method. So again, Jacobi's method, I'm taking P to be the diagonal part. Let me make that explicit, and let me take the matrix that we know the best. I'll call it K. So K, or A, this is the A, is my friend with 2's on the diagonal, minus 1's above. I apologize. Well, I don't really apologize, but I'll pretend to apologize for bringing this matrix in so often. Do we remember its eigenvalues? Guess we computed them last semester, but that's another world. I'll say what they are. The eigenvalues of A, this is an M now. The eigenvalues of this matrix A, well, I see 2's on the diagonal, right? So that's a 2. That accounts for the diagonal part, 2 times the identity. Then I have a minus, and then the part that comes from these 1's, which are forward and back. Well, what would von Neumann say? What would von Neumann do with that matrix? Of course, he would test it on exponentials, and he would get 2 minus e to the ik minus e to the minus ik, and he would put the 2 exponentials together into cosines, and that's the answer. It's 2 minus 2 cosine of whatever angle theta. Those are the eigenvalues. The jth eigenvalue is the cosine is at some angle theta j. It's worth, since maybe just to take again a minute on this matrix. So the eigenvalues are between 0 and 4. The eigenvalues never go negative, right? Because the cosine can't be bigger than 1. And actually, for this matrix, the cosine doesn't reach 1. So the smallest eigenvalue is 2 minus 2 times that cosine close to 1. So it's too close for comfort, but it is below 1, so the eigenvalues are positive. And they're between 0 and 4. At the other extreme, when theta is near pi, the cosine is near minus 1, and we have something near 4. So the eigenvalues of that if you look at that matrix, you should say, yeah. Special matrix eigenvalues in this interval 0 to 4. And the key point is how close to 0. Okay, now what about M? Well, what about P first? What's P? For Jacobi, so P for Jacobi is the diagonal part, which is exactly 2i. So that's a very simple diagonal part. Very simple P. But it produces a matrix M. You remember M is the identity matrix minus P inverse A. That's beautiful. So P is just 2i. So I'm just dividing A by 2, which puts a 1 there, and then subtracting from the identity. So it has zeros on the diagonal. Well, that's what we expect. It will be zeros on the diagonal. And off the diagonal, what do I have? Minus, with that minus, P is 2, so it's a half. It's a half off the diagonal. And otherwise all 0. That's the nice matrix that we get for M in one dimension. Oh, I have to say, of course, as you know, we wouldn't be doing any of this for this one-dimensional matrix A. It's tridiagonal. We can't ask for more than that. Direct elimination would be top speed. But the 2D case is what we understand, that it has a big bandwidth because it's two-dimensional, three-dimensional even bigger, and the eigenvalues will come directly from the eigenvalues of this 1D case. So if we understand the 1D case, we'll knock out the 2- and 3-dimensional ones easily. So I'll stay with this one-dimensional case where the matrix M, and I'll even maybe should write down exactly what the iteration does. But if I'm looking now at convergence, do I have or don't I have convergence, and how fast? What are the eigenvalues, and what's the biggest one? Well, the eigenvalues of A are this, and P is just, P inverse is just 1/2 times the identity. So what are the eigenvalues? Well, again, I know the eigenvalues of A, so I divide by 2. Let me write down what I'm going to get now for the eigenvalues of M. Remembering this connection. So the eigenvalues of M are 1 minus 1/2 times the eigenvalues of A. Yeah, I better write that down. 1 minus 1/2 times the eigenvalues of A. Of course, it's very special that we have this terrific example matrix where we know the eigenvalues and really can see what's happening. And we know the matrix. Okay, so what happens? I take half of that. That makes that a 1. When I subtract it from that 1, it's gone. When half of that 2 is canceled, I just get cos theta. Theta sub whatever that angle was. It's a cosine. And it's less than 1. So convergence is going to happen. And convergence is going to be slow or fast according as this is very near 1 or not. And unfortunately, it is pretty near 1. Because the largest one, I could tell you what the angles are. That's to complete this information, I should have put in and von Neumann got them right. And that's J, is there maybe a pi over n plus 1? I think so. Those are the angles that come in, just the equally spaced angles in the finite case. So we have n eigenvalues. And the biggest one is going to be when j is 1. So the biggest one, rho, the maximum of these guys, of these lambdas, will be the cosine of when j is 1 pi over n plus 1. That's the one that's slowing us down. And notice the eigenvector that's slowing us down, because it's the eigenvector that goes with that eigenvalue that's the biggest eigenvalue that's going to hang around the longest, decay the slowest. And that eigenvector is very smooth. It's the low frequency. It's frequency 1. So this is j equal to 1. This is the low frequency. J equal 1, low frequency. The eigenvector is just samples of the sine of a discrete sine. One lowest frequency that the grid can sustain. And why do I emphasize which eigenvector it is? Because when you know which eigenvector is slowing you down, and here it's the eigenvector you would think would be the simplest one to handle. This is the easiest eigenvector. Higher frequency eigenvectors have eigenvalues that start dropping. Cosine of 2 pi, cosine of 3 pi over n plus 1 is going to be further away from 1. Now, I have to admit that the very highest frequency, when j is capital N, so when j is capital N, I have to admit it happens to come back with a minus sign, but the magnitude is still just as bad. The cosine of n pi over n plus 1 is just the negative of that one. So actually we have two eigenvalues that are both hitting the spectral radius, and both of them are the worst, the slowest converging eigenvectors. And this eigenvector looks like very smooth, and the eigenvector for that high frequency one is the fastest oscillation. Yeah, if I graph the eigenvalues, I'll graph the eigenvalues. And you'll see that it's the first and the last that are nearest in magnitude to 1. Okay. I was just going to say, all right, can I anticipate multigrid for a minute? So multigrid is going to try to get these guys to go faster. Now this one can be handled, you'll see, by just a simple adjustment of Jacobi. I just weight Jacobi a little bit. Instead of 2i, I take 3i or 4i. 3i would be good. 3i would be very good for the preconditioner. And that will have the effect on this high frequency one that it will be well down now, below 1. But this will still be the slowpoke in converging. And that's where multigrid says, okay, that's low frequency, that's too low, that's not converging quickly. Take a different grid on which that same thing looks higher frequency. Well, we'll see that. See it tomorrow. Okay. All right, so if I stay with Jacobi, what have I learned? I've learned that this is rho. For this matrix, the spectral radius is that number, and let's just see how big it is. How big is, that's the cosine of a small number. So the cosine of a small number, theta near 0, the cosine of theta is 1 minus, so it's below 1, of course, a half theta squared. Theta is pi over n plus 1 squared. All this simple estimates really tell you what happens when you do Jacobi iteration, and you'll see it on the output from. I mean, you can, I hope will, code up Jacobi's method, taking P to be multiple of the identity. So very fast. And you'll see the convergence rate you can graph. Oh, here's an interesting point. I'll make it again. What should you graph in seeing to display convergence and rate of convergence? All right, let me draw a possible graph here. Let me draw two possible graphs. I could graph, this is K, as I take more steps. I could graph the error. Well, the size of the error. It's a vector, so I take its length. And I don't know where I start at E naught. This is K equals 0. This is the initial guess. If I use, well, I'm going to draw a graph which you'll draw much better by actually getting MATLAB to do it. Before I draw it, let me mention the other graph we could draw. This tells us the error in, this is the error in the solution. You might think that's the natural thing to draw. It is. But we could also draw the error in the equation, the residual error. So I'll just put up here what I mean by that. If I put in, so AX equals B exactly. AXK is close. And the residual is, let me call it R, as everybody does, is the difference, AX minus AXK. It's how close we are to B. So it's B minus AXK. The true AX gets B exactly right. The wrong AX gets B nearly right. So you see, because we have this linear problem, it's A times the error. X minus XK is EK. So this is the residual. And I could graph that. That's how close my answer comes to getting B right, how close the equation is, where this is how close the XK is. So that would be the other thing I could graph. RK, the size of the residual, which is AEK. Okay. So now I have to remember what I think these graphs look like. But of course, it's a little absurd for me to draw them when I think what we see is that the residual drops pretty fast. The residual drops pretty fast and keeps going. For, let's say, Jacobi's method, or in a minute, or maybe next time, another iterative method. But the error in the solution starts down fast, and what's happening here is the high-frequency components are getting killed. But those low-frequency components are not disappearing, because we figured out that they give the spectral radius the largest eigenvalue. So somehow it slopes off, and it's the price of such a simple method is that you don't get great convergence. Of course, if I put this on a log-log plot, the slope would be exactly connected to the spectral radius. That's the rate of decay. It's the EK is approximately, the size of EK is approximately that worst eigenvalue to the kth power. Do you see how this can happen? You see, this can be quite small. The residual, quite small. I think it's just very important to see the two different quantities. The residual can be quite small, but then how would I, from the residual, if I wanted to get back to the error, I'd have to multiply by A inverse. And A inverse is not small. Our matrix A is has eigenvalues close to 0. So A inverse is pretty big. A inverse times AEK. This is small, but A inverse is like, picks up those smallest eigenvalues of A, picks up those low frequencies, and it's bigger. Slower to go to 0, as we see in this picture. So it's this picture that is our problem. That shows where Jacobi is not good enough. Okay. So what more to say about Jacobi? For this matrix K, we know its eigenvalues. The eigenvalues of M, we know exactly. The matrix M, we know exactly. Do you see in that matrix? And now, if I had said, look at that matrix, and tell me something about its eigenvalues, what would you say? You would say it's symmetric, so the eigenvalues are real. And you would say that every eigenvalue is smaller than 1. Why? Because every eigenvalue is, if you like to remember this business of silly circles, every eigenvalue is in a circle centered at this number, in other words, centered at 0, and its radius is that sum of those, which is 1. So we know that every eigenvalue is in a circle of radius, in the unit circle, and actually it comes inside the unit circle, but not very much, only by 1 over n squared. And what do I learn from this 1 over n squared? What power, how many iterations do I have to take to reduce the error by, let's say, 10 or E or whatever? If the eigenvalues are 1 minus a constant over n squared, I'll have to take the n squared power. So if I have a matrix of order 100, the number of iterations I'm going to need is like 100 squared, 10,000 steps. And that's, every step is fast, especially with the Jacobi choice. Here's my iteration, and P is just a multiple of the identity here. But, so every step is certainly fast. Every step involves a matrix multiplication. And that's why I began the lecture by saying matrix multiplications are fast. A times xk, that's the work. And it's not much. It's maybe 5 non-zeros in A, so 5n, that's fast. But if I have to do it 10,000 times just to reduce the error by some constant factor, that's not good. Okay. So that's why people think, okay, Jacobi gives us the idea. It does knock off the high frequencies quite quickly, but it leaves those low frequencies. Well, I was going to mention weighted Jacobi. Weighted Jacobi is to take, instead of P, put in a weight. So weighted Jacobi, let me put this here and we'll come back to it. So weighted Jacobi simply takes P to be the diagonal over a factor omega. And for example, omega equals 2/3 is a good choice. It happens. Well, let me draw you can imagine that if this is 2 times the identity, so it's just 2 over omega I. So I'm just choosing a different constant. I'm just choosing a different constant in P, and it has a simple effect on M. I'll draw the picture. The eigenvalues of M are these cosines. So I'm going to draw those cosines, the eigenvalues of M. So they start, I'll just draw the picture of cos theta if I can. What does a graph of cos theta look like? It's somewhat, dear me, from 0 to pi. So I'm going to see this is theta equals 0. This is theta equal pi. If I just draw cos theta, please tell me if this isn't it. Is it something like that? Thanks. And now, where are these? Theta 1, the bad one, theta 2, theta 3, theta 4, theta 5, equally bad down here. So there's cos, there's the biggest one. That's rho, and you see it's pretty near 1. And here I'm going to hit, at this frequency, I'm going to hit minus rho. It'll be, again, near 1. So the spectral radius is that's rho. The cosine of that smallest angle, theta over n plus 1. And what happens when I bring in these weights? Well, it turns out that, so now the eigenvalues of M with the weights will be 1, it turns out 1 minus omega plus omega cos theta. Very, you'll see it in the notes. No problem. So it's simply influenced by omega. Like if omega is 2/3. If omega is 2/3, then I have 1 minus omega is 1/3 plus 2/3 cos theta. That's what, instead of graphing cos theta, which I've done, so let me complete this graph for cos theta. The eigenvalues unweighted with weight omega equal 1. Now it's this thing I draw. So what happens? What's going on here? For a small theta, cosine is near 1. I'm again near 1. In fact, I'm probably even a little worse. Probably up here. But I think it goes down like that. So it starts at near 1, but it ends when theta is pi. This is 1/3 minus 2/3. It ends at minus 1/3. You see, that's a lot smarter. Where this one ended at minus 1. That one ended at near minus 1, but this one will end with omega. This is the omega equal 2/3, the weighted one. All you've done is fix the high frequencies. Well, when I say all, that was a good thing to do. The high frequencies are no longer a problem. The low frequencies still are. So the only way we'll get out of that problem is moving to multigrid. Okay, can I, in the remaining minute, report on Gauss-Seidel? And then I'll come back to it. But a quick report on Gauss-Seidel. So what's the difference in Gauss-Seidel? What does Gauss-Seidel do? It uses the latest information. As soon as you compute an x, you use it. Where Jacobi computed had to keep all these x's until it found all the new x's. But the Gauss-Seidel idea is, as soon as you have a better x, put it in the system. So the storage is cut in half because you're not saving a big old vector while you compute the new one. And I'll write down Gauss-Seidel again. So it's more up to date. And the effect is that the Jacobi eigenvalues get squared. So you're squaring numbers that are less than 1. So Gauss-Seidel, this gives the Jacobi eigenvalues squared. Well, the result is that if I draw the same curve for Gauss-Seidel, I'll be below, right? Essentially, a Gauss-Seidel step is worth 2 Jacobi steps, because the eigenvalues get squared as they would do in 2 Jacobi steps. If I do Jacobi twice, I square its eigenvalues. So it seems like absolutely a smart move. It's not brilliant, because this becomes cosine squared. I lose the 1/2, but I'm still very, very close to 1. It still takes order n squared iterations to get anywhere. So Jacobi is, like you could say, replaced by Gauss-Seidel as being 1 step better, but it's not good enough. And that's why the subject kept going. This gives rho is 1 minus order of 1 over n, first power. Where these were 1 minus 1 over n squared. So this is definitely further from 1. And then this can be way further from 1. So you can see some of the numerical experiments and analysis that's coming. Okay, I'll see you Wednesday to finish this and move into Multigrid, which uses these.